Hello, my name is Rodney Rocha. I work within the Structural Engineering Division at the NASA Johnson Space Center in Houston, Texas. Before, during, and after the Columbia mission and accident, that was shuttle mission STS-107, I had the role of Chief Engineer for Space Shuttle Orbiter, serving the Structural Engineering Division. Within that role, there was a lot of comprehensive responsibility for hardware, but also the critical math models and test data that were associated with the orbiter and space shuttle system. Given that math models may be used incorrectly in the decision-making analysis or the assessment, it is possible that a flawed decision could be made regarding the preparation of the vehicle, its processing, the flight readiness process, or a decision during the mission. Critical math models have different reasons to be utilized, and they can be generally put into different phases of usage. That could be the early design phase, where the math models have some level of high uncertainty, and there's a high level of conservatism also. They could be math models used for assessing the processing of the vehicle and its readiness for flight. There could be in-flight math models too. One of the most difficult math models to work with or to develop are damage tolerance models. They sometimes have to be highly specialized. They may not have existed before because damage to a space vehicle before launch or during the launch or on orbit or in space may never have been seen before, and there's a unique configuration or level of damage associated with it. So special models and test data might have to be developed for such cases. Critical math models need care and feeding. They need formal review, and sometimes they need updates to follow the design changes that may be implemented or the mission operations and flight rules, things like that may change. So math models should follow those kind of changes and be updated appropriately. There are times where the actual flight situation or an event or an anomaly has occurred where the critical math model may be very well within its bounds and the configuration of what has happened where it's entirely appropriate to be applied. There are other situations, usually in the realm of damage tolerance assessment, where we have to be very careful about not violating the assumptions or the constraints put on the model and any limitations. We have to be very aware of those and be careful that we do not misapply the model in those cases. All math models have limitations within them. There could be variations in material response. There could be variations in the levels of uncertainty. There could be differences between and among the vehicles. There's also variability in the environments that cause a vehicle response. Those kind of things work into the uncertainties of a critical math model. We should be aware of them when we use the math models of environments and vehicle when we're using them to be combined together, and we also have to inform management that those are cautions and warnings when attached to any engineering recommendation that we may give. To some extent, in structural engineering, my profession, we take care of some of that early on in a phase called the factor of uncertainty applied to models. Those are usually relaxed to 1.0, where essentially not having a factor of uncertainty as the vehicle and all the processes and testing mature to get us to a mature vehicle for operation. But one thing we keep all the time is the so-called factor of safety. That lets us account for environmental exceedances to some extent, some load exceedances, and also for material property variations within the vehicle. We retain those all the time. Having confidence in the critical math model and its maturity, or to some extent related to how much resources and funding we had available, how much time we were given within a program schedule to get everything together, and sometimes it has to do with just the state of the art at the time. For example, the early shuttle models, the structural finite element models, had to be low resolution and low fidelity simply because the computers at that time were not capable enough. Today, they are. However, every model can suffer from a certain level of uncertainty if there is no test validation behind it. What I mean by that is that every math model put together has to have some testing with measured data that agrees with the math model. If there's no or significant disagreement, there is retuning of the model, or it's updated or corrected in the areas that need such. But every math model needs some degree of test validation behind it. When we fly space vehicles over and over, we collect data called, they're flight measured data. We say that kind of data or observations are in family if we think they are somewhat statistically clustered, they look reasonable for the flight, and they're relatively consistent with the certification and the math models that the predictive math models for that flight and for that event. And we call that in-family data. The interesting thing happens is if we get a piece of data or an observation called a poke out and it's out of family, that sometimes and appropriately caused us to say, why did that happen? What is causing that? And sometimes the program, like the Space Shuttle program, would then request that we do a flight reconstruction. Now we're relying back on our predictive math models, trying to recreate what flight events were occurring at that time, the complex combined environments, and we rely again on our math models to try to explain and elaborate on the out-of-family situation. I should also point out that in-family data is not necessarily indicative of having margin for flight. We never really know the margin in in-flight data. You might feel good if you were flying within the certification limits, but the in-family data alone does not really indicate margin. It just says that you're consistently flying and experiencing something pretty typical over and over again. Our radar level goes up when we get an out-of-family situation. It's a responsibility of engineers who may have been part of the history and development of those math models to assure management or to explain to them how the math model is to be used appropriately, the embedded assumptions, the limitations and constraints for those applications. It might result in maybe not a black or white recommendation, a yes or a no. It may not do that. It may be a gray set of options, but all those would be discussed, what the limitations and constraints are, what the options would be, and we might continue further investigations if we were to be given actions. There's always the opportunity or opportunity to misuse a critical math model and fall into a pitfall of misuse, a flawed recommendation, an inaccurate statement about the usage of such math models. We have to consider safeguards in the form of control and mitigation. Sometimes that can be by assuring that critical math model has enough conservatism and safety margin built into it, that we are very clear during the development of that math model about its limits, the embedded assumptions, and the bounds on its usage. We also have to recognize that sometimes even in-family flight experience does not necessarily say we have positive margin. It just says that we're flying in a typical manner, and we really don't know the margin from that kind of clustered data, though it looks reasonably clustered together. We have to use caution in the way we express what the model can do and not do. We have to safeguard ourselves against biases that say that based on looking at some set of data that things look fine, but if we haven't really done an extensive assessment yet by bringing all of the math models that we could to bear, there could be another outcome to that. Kind of underlying all this is who does that. Typically in past programs and hopefully for future programs, We're relying on an engineering community, sometimes called a technical community of practice, that are familiar with the math models. They were part of the history. They were part of their development. They were part of their defining what the limitations were. They were part of the test programs. That could be a NASA contractor team, and they fashioned what they call the critical math model. They know its bounds, and they know its correct usage because they were part of it. When the assessments done by the engineering community or the technical community of practice are finished and ready to present, they're usually in the form of recommendations to management. In past programs, they could have been the mission management teams like used in the Space Shuttle program. We think that management has the obligation to fully vet those recommendations, to understand them, to ask a lot of questions. It's appropriate to levy more actions, to get even more data, more assessments, more usage of the math models, or to bring it all to a close. We in the engineering side recognize that they always have the prerogative to make the decision in the end. We feel it's our obligation to keep them fully informed based on data, whether it's the test data or the critical math models or a combination of both, that they fully understand that and the failure modes that could ensue. Let's consider a lesson learned from Shuttle Mission 107, the Columbia accident. In that scenario, the debris assessment team that was to analyze the bipod foam release from the external tank, and we now know that that's subsequently hit at 500 miles an hour. We think wing leading edge panel number 8 on the left wing and caused a big hole, but we only know that from months later after the accident. But during the mission, the debris assessment team, of which I was a part as chief engineer for the structural engineering division, were given very limited time to produce an assessment as to what had just happened. We all recognized immediately, the engineering team made up of NASA, contractors, and safety, aerodynamicists, structures people, and so on, and people from engineers from Michoud facility, that we could not initiate a credible analysis to even employ our math models because we knew virtually nothing about the extent of the damage, if any, or exactly where that foam projectile hit. There was just subjective and weak evidence that it had hit here or there. There was no video enhancement, so we felt crippled right away that we couldn't even initialize a credible analysis, even if our math models were appropriate. So the first order of business is to try to get an image, a photo, something better that said, there is no doubt it hit here, and here is the damage. That kind of request that went to shuttle management was denied. It did not happen. There were members of the debris assessment team that asked for such data. It did not happen. There were others asking too. It did not come forward. Therefore, we were forced into the unpalatable situation of having to use the models we had. That included the crater model, which is an empirical tool based on foam strikes, test data, foam strikes hitting tiles, but within a certain limit, very tight limits on the mass, volume, and speed of that particle. What hit Columbia was hundreds of times larger, so we were way out of bounds and therefore not really in the proper application regime for using crater. The same could be said for the ICE program that was utilized somewhat for the carbon panel. If there was a piece of foam hitting, a large piece of foam hitting the wing of the orbiter, Columbia. But again, that model was out of bounds or was not really appropriate. It was developed for ice droplets that would cause coating damage or cracks onto an RCC panel. That clearly was not the material that was shed during that mission. It was foam, and the model was inappropriately used. There was also a third engineering, probably more of an engineering argument or rationalization about what if the foam had hit a landing gear door seal, which has a ropey material that protects the interior of the landing gear wheel box from hot gas entry during entry into the atmosphere. If that seal were pushed aside by a foam projectile, hot gas could enter, cause the tires to overheat and explode. So that kind of assessment even had more of an engineering argument applied to it. So all three models were really out of whack. They were inappropriately used. We think it was due to the time pressure. There was only 2 or 3 days to respond to the mission management team. There was a lot of uncertainty as to the actual damage that was there. We had to postulate that and thinking that we had to keep it conservative but not too conservative. But we were forced into that posture. We were between a rock and a hard place. We had no data to help guide us into that. So the debris assessment team produced a flawed analysis. We will admit that. But we also feel we were pressured to do so because we were denied other assets and data that could have helped us. There is a painful lesson that comes out of this Columbia scenario and the debris assessment team of which I was a part. The lesson to me, and I think others might agree that were on that team, is that we fail to fully inform upper management that we were hamstrung and that whatever analysis we brought forward, and we brought forward some, was really a hypothetical case that we could not verify. We devised some cases that appeared on the one hand to be conservative or reasonable, but really had no basis whatsoever. There was no image to show us the real damage. I think we could have been and should have been more forceful in saying, we really don't know. Here is a case that we've devised. We're going to show it to you, but we can't verify that it has any semblance whatsoever to reality. I think we should have come forward with alternate or dissenting opinions, or maybe a statement that we really can't make an assessment. There is no credible assessment that can be done. We are so way out of bounds and in a state of ignorance about this situation, and we are telling you that there's nothing more we can do. You upper management are going to have to consider stronger action now. Either get a photo, consider a rescue mission, get the crew involved, whatever, a repair, an attempted repair. Let us focus our energies on those things. But we did not, and the painful lesson is that we did not, but we learned. Another valuable lesson, in addition to the Columbia accident mission, was a return-to-flight mission, some flights after in return-to-flight, called STS-118. In that case, a piece of ice, probably originating from the external tank, during ascent became liberated and flew and hit the underbelly of the orbiter and producing deep damage. Ice projectiles tend to produce not great surface area damage, but very deep penetrating damage. In fact, it went all the way down. We know this from photographs, all the way down to the bonded layer, where you could see some different coloration of the strain isolation pad and the bonding agent down there. Very quickly, that area was scanned with our new image assets, with high-resolution photography, and even the lasers were able to map that area with a three-dimensional model that was transmitted to the ground, and a test tile for a potential lab test was created on the ground at the machine shop. They created exactly the same of gouging that was on orbit, on the orbiter. The question was, is a test appropriate for this case? Should we test this in the arc jet, which is a 10 megawatt spark plug? It heats air to superheated temperatures, attempting to simulate to some extent hot gas entry into the atmosphere. Thermal engineers know that test facility, there's one here at JSC, but there's also one at Ames, and there's others around the world. They are not complete simulations of hot gas entry. You can match certain key parameters, and you take your pick on what, there's like a half dozen of those, which ones you want to match. The others, they cannot be matched. Those are limitations from any test facility. So There were some cautions about expressed to management from our thermal engineers. We're going to have to be very careful about testing because they can give you results that you may not like. The ArcJet facilities tend to be very severe. The boundary conditions aren't right, or the boundary layer flow isn't right. You may not match all the parameters. And also, what type of heating do you, the worst kind of heating based on this type of condition or another? We must not overly state or have an overly severe condition. However, in the end, we had a severe condition. The test results from that ArcJet test with tile and aluminum plate structure that the tile was bonded to, well, exhibited puzzling results. It showed more damage, some cascading damage, some debonding of neighboring tile. We had to go back. Our thermal engineers, who are the experts here in aerothermal, the heating rates, and also tile and what the bonding limits are on temperatures for bonding to aluminum structure, they all pointed out that these puzzling results were expected in this severe test, but they are not to be expected from the actual flight entry. They relied instead on their flight experience and their confidence in the math models and the certification of that system, and the way they thought that flows and how they interacted and the boundary layers of real flow and a real flight would act as opposed to what the facility would do. In the end, they were right. The recommendation was no repair was necessary based on their engineering arguments and experiment, even though the ArcJet showed more damage that could occur and possible cascading damage. They had to stick to their ground and their reliance on their experience and what they knew of the thermal protection system to say the ArcJet overstated this. And it was a healthy debate. There was a lot of tension on this. There was a dissenting opinion expressed at the mission management team. One of those came from myself about repair. But in the end, all was vetted. A lot of words were said. Everyone was listened to, and there was trust expressed by the mission management team and the confidence of the thermal engineers. No repair was necessary. There would be no more damage, no progressive damage. And we landed safely, and they were right. There was no progressive damage. This illustrates how a test can be misapplied also. It can be too severe. We all know what can happen when it's unconservative, but in this case, it showed more damage than really did occur. Yet another interesting flight that taught us some valuable lessons of a different kind was STS-117, another flight in the return to flight period after the Columbia accident. In this case, during shuttle ascent, the thermal blanket, a flexible blanket, unstitched itself and flipped upwards, exposing the honeycomb aluminum structure underneath. That OMS pod, that stands for Orbital Maneuvering System pod. Within there are propulsion tanks like helium tanks and fuel tanks for operating engines on orbit. It's a big bulbous structure. They look like big lobes at the base of the vertical tail of the orbiter. There was a possibility here, when using our math models to assess the structural integrity of that area, that the honeycomb aluminum may have been severely degraded. It had lost over a certain piece of acreage the insulation protection from that blanket. It had flipped upward. So it was exposed to some degree of ascent heating. Did that damage the honeycomb aluminum or not? That honeycomb aluminum, it's a wafered, multi-wall, thin piece of aluminum, probably a 1/4 inch thick or even thinner, with face sheet on it. It is vented with tiny holes, so it allows the air inside to vent and equilibrate with the decreasing air pressure outside, so you don't overpressurize the internal cells and they'll burst. So there are venting holes by design built into that structure. But that also allows water vapor to enter in there, and if you expose yourself to more heating, like ascent heating, it's possible that that water, being now steam, is bursting cells during the ascent. So there was a possibility, as indicated from our models, that we had degraded that area structurally, that it had lost a lot of its structural integrity. There was a multi-center team to assess this, a structures team from Johnson Space Center, I think from Ames, and also from Glenn Research Center, working on all this together with the appropriate math models. However, the difference between we're good, there was not significant ascent heating damage, or we're no good, depended on the residual amount of insulation that was still bonded. There was a strain isolation pad, this little foamy, spongy stuff that was still bonded at some critical areas. The question was how thick. The models required to show good a certain minimum thickness, and that would say that the structure would have been protected from damage, structural damage caused by heating. If we were underneath, or if that residual insulation thickness was smaller than that, there was the real possibility of no structural integrity left, and even a repair. Even if the EVA astronauts would have repaired the area, it might not be good enough, and that there was a possibility that there would be cascading damage during entry and descent. The OMS pod structure might continue to deform, droop downward. Hot structure would touch the composite overwrap pressure vessels, helium tanks, propulsion tanks, fuel lines, electrical lines, and so on. It would continue to deform, and maybe a hole would open up. We didn't know that. So it all hinged, is the remaining insulation thick enough or not? We could not answer that from the photographs. They really weren't good enough. The EVA astronaut did take some. There were some descriptions from that astronaut, but the illumination or shadowing or something was not good enough at that time. The mission management team was very distressed, and so were we. We were at an impasse. We could not give a recommendation because we did not know that critical remaining dimension of the insulation. So we took a 2-hour break, and it turned out at the end of the day it was engineering experience and a reliance on math models of an intact structure that saved the day. The TPS thermal engineers, NASA and contractor, were able to put their heads together and determine from their experience in interpreting with their eyes and their experience that there was indeed enough insulation. There was at least or beyond the critical dimension. That let us rely on our math models again. We were good. We were able to stitch it up with an EVA and return. We landed safely. Everything was okay. But it all hinged on one piece of data, one piece of software, soft goods, a thermal insulation layer being thick enough or not. And it was the difference between the math models are no longer applicable anymore, or they're good because we can now show that we had enough insulation to prevent heat damage. So we returned safely from that mission. I don't think there were any other detrimental effects observed after we landed. So it was a good call, but it was a very tough call. It was a very distressing time. We reached the end of our math model application, but it all hinged on a critical dimension, yes or no, the difference between good and bad. I have a final lesson learned based on multiple scenarios. There were things piling up in 2002 and also during return to flight. Things like the flow liner cracks. These were cracks in the main propulsion lines that feed the main engines of the Space Shuttle orbiter. There were the Beaster ball cracks. That's a ball strut tie rod assembly joints that hold the feed line stable, structurally stable, on the massive 17-inch diameter feed lines that feed propellant and oxidizer to the engines. There were the salad bowl dents. There were the material property discrepancy on the solid rocket booster external tank assembly ring. That ring holds the struts to the external tank in between the booster. There were other kinds of damages that were occurring to the RMS. There was an operator or technician that ran a platform into some of the composite material. In all of those scenarios, there wasn't necessarily a standby critical math model ready to use. That's again that world that's very difficult called damage tolerance. It tends to be unique, like I've said before. It puts the hardware out of configuration, and so your critical math models may not apply. Whatever you did to certify may not apply anymore. So it may be absolutely necessary to create new math models. So that brings me to this other point as a lessons learned. Who does that? We believe it's the sustaining engineering. Those are those engineers that have ownership in the hardware or the environments, the test programs, and the math models. They were there from probably the design process very early, and also certainly through the certification process. They're familiar with the test data, all that before the vehicle ever flew. They are familiar with anomalous results, design changes, material changes, so on. They were part of the development and creation generation of those critical math models, so that when we get a unique situation, they can also be part of what new would have to be created. A new math model, a new tool, a new test that is customized or ad hoc to that very situation. Just to take one of those examples I gave, like the flow liner, that was an exceedingly complex situation. To an outside observer, someone new, they'd say, well, I just see cracks in a metallic sheet metal, so what? The question was, what caused the cracks? How long did it take to generate those cracks? One mission? Several missions? How much do I have left? How much life? What happens when a crack runs all the way through it? Now you have pieces of metal potentially entering the engine and causing a catastrophic explosion. It turned out in the end we needed multiple disciplines from every area you can think of. Probably not flight control, but structures, fracture mechanics, thermal, cryogenics, fluid dynamics, modal analysis, random vibration, modal vibration, stress, strain, instrumentation, computational fluid dynamics, coupling to forcing frequencies and a dynamic forcing function. All those led to weeks and months of meetings and coalescing to what the final actions would be to get us out of that situation. The shuttle was grounded for several months in 2002 because of that very problem. There were new math models, new insight that were brought to bear, and more testing. It led to a pretty much revolution in that, in looking at applying new tools and the computer power of modeling and simulation at several levels to get us out of that problem. There was also reliance on engineering argument and what could couple to this, or what was important and what was not important. That sometimes guides what kind of math models you need. What is important? What is not important? What is it that I don't have to model? But those examples and others are illustrative of a complex aerospace vehicle where, even though you thought you've made a good job in trying to anticipate everything in design and certification, it turns out there can be surprises, and sometimes they have pretty painful consequences. So there's always the opportunity to see something new, especially in the area of damage tolerance, where you may have hundreds or thousands of math models at your disposal, but damage tolerance can throw you into a new one. I need more math models. I need new test data. I need more insight. And hopefully programs are receptive to that and will apply their appropriate resources. So underneath all that, too, is the importance of sustaining engineering. It's those engineers that are part of the process, the long process that, or maybe it started in design or maybe in certification, maybe in the early flight test, but they were available because they know the hardware, they know the environments, they know the math models, they know their limitations, and they know what to do next and communicate maybe with others that are part of the action. Without those, I'm afraid that you just have consultants and advisors. They don't have the insight, they do not have the history. The number one takeaway after all of this that I'd like to communicate is math models have inherent limitations and embedded assumptions. Part of being an engineer and expressing recommendations to management is to point out those limitations. No math model is a complete simulation of Mother Nature. It always has inherent limitations. But if it becomes part of a safety or flight decision process to avoid flaws and misapplications in its use, you have to be ready to stand up and defend that model, and also to alert everyone that these are the limitations. We're going beyond its usage, or it should not be used, or maybe in damage tolerance, we need to create something new. And this is what it should look like. Something new would have to be developed, or a new test. For more information, or if you would just like to contact me with more questions, or just want to express things to me, you can contact me, Rodney Rocha, at the Structural Engineering Division. That's code ES6 at the NASA Johnson Space Center in Houston, Texas.